Welcome to the Volumetric video workshop, which was created in collaboration with Film Academy and Dimension. And this workshop is split into 2 days and or into 2 parts, into the theory presentation part, which I'm recording now, and the hands-on part, which will be in the second video, and it will include some workflows in Houdini. And this workshop is about fundamental concepts and papers related to volumetric video. And I will try to present the current volumetric video landscape and some relevant research. However, I have a limited biased knowledge of the field and the research behind it, so I'm likely to miss some important things. And I borrowed images from many great presentations and papers, and you can find sources below figures. And all information I mention here is publicly available. So a bit about me. So I am Yurai Tomori. I am software developer at Dimension. Before I graduated from Film Academy Technical Directing Studies, and I'm interested in graphics, vision, pixels, voxel polygons, and related fun stuff. And please get in touch with me. Here you can find links. And there are quite a few things in this presentation, and at start we will talk about what is a volumetric video. We will talk about the key properties of a volumetric video system or a free viewpoint video. I will talk about dimension, then approaches to volumetric video, products, studios, tools, and then I will give a high-level overview of the full volumetric video production pipeline. So we'll start talking about acquisition, processing pipeline, coding and transmission, post-processing, rendering, delivery, and we'll also discuss current bottlenecks and future prospects of the medium. So let's introduce the volumetric video, and let's talk about fundamentals and a bit of history. So origins of volumetric video can be traced back to the 19th century, when Nadar, French photographer, already explored spatial domain. So here in this example you can see the autoportrait, which is shot from multiple cameras, from multiple angles, but it's shot at the same point in time. There were also some other efforts, and where they tried to capture multiple angles of the same time moment to aid with sculpting. So, for example, those photo sculptures. And then on the other hand, there was Edward Muybridge, who explored temporal domain. So here you can see again multiple cameras, but they are capturing different points in time. And one way to look at it is that the temporal domain evolved into the cinema, and spatial domain had to wait for technology and eventually evolved into photogrammetry and volumetric video. And if you are interested more in the history, I highly recommend Tim Macmillan's RTC talk. So free viewpoint video is a type of filmed content that supports viewing with 6 degrees of freedom. And three-dimensional production from multiple view video or 3D video was first popularized by Kennedy et al., who coined the term virtualized reality. And there have been papers in 1997 and 1998 that introduced the topic of virtualized reality and volumetric video. So those 2 papers are really interesting, and they discuss fundamental concepts and the principles they describe. are pretty much still in use today. So the first one is virtualized reality, constructing virtual worlds from real scenes, and the second one is constructing virtual worlds using the stereo by Takeo Kanadi, Peter Radner, and Mr. Narayan. And motivations behind virtualized reality include shortcomings of media, including director-decided viewpoints and 2D views. And virtualized reality is trying to address that, and it's an immersive medium which lets a user pick his own viewpoint and display the captured content in stereo or in VR or AR. The virtualized reality process involves 3 phases. So first we need to capture or transcribe the visual event, then we need to process it or recover 3D structure, and then we need to render it or generate synthetic novel viewpoints. And research in this area combines computer graphics, computer vision, and visual communications, and it spans the whole media processing chain from capture to display. And the design of system has to take all parts into account, so it's quite a complex topic, and it requires it's built on top of research in many research areas. And before diving too much into the theory, let's take example capture. So this is a sample capture then provided by Dimension, and here we will be able to see a couple of we will be able to notice a couple of things, and during the presentation I will elaborate more on them. So we can see that the capture is 3D. We can rotate it arbitrarily, or we can view it from any viewpoint. And this capture consists, or output of this capture consists of a sequence of geometries and texture maps. And something to notice is that the polygon density is higher at phase, which allocates more data to this part of body, which helps with perceived quality. And also something else to notice is that there are topology changes in geometry, so they don't happen on each frame, but there are sequences of meshes which share the same topology. So here you can see those changes, but when previewed with the texture, though, those topology changes are not visible. And volumetric video comes under multiple names. So they include 4D, 3D video, holograms, free viewpoint video, virtualized reality, holographic video, and so on. And throughout this presentation I will use free viewpoint video and volumetric video terms interchangeably. And although free viewpoint video has been studied in academia for more than 2 decades, cumulative improvements in bandwidth requirements and quality mean it is now practical for use in production context. So for a long time it hasn't been really practical or commercially viable to produce such content, but now the technology advanced and it's starting, or it's already there. So possible applications that were discussed in those early papers of virtualized reality include realistic training in a virtualized workspace through telepresence and imaginative uses in entertainment. And it was really interesting finding when I found this suggestion or prediction in the paper, and then I found volumetric video projects that are quite recent, and they are matching those those possible applications that were predicted in the paper. So the first one is volumetric video training, which includes volumetric capture of of the training material. It is a learner-directed experience, and it explains a complex process that needed to be shared quickly and widely. It's done by Dimension and others, and you can see that if we produce training material in a 3D video, then this might be more intuitive or quicker to learn for people, because they have the freedom to choose their viewpoint. And you could imagine that if this training video was captured in 2D, then the audience would maybe struggle with seeing details from the behind, or they wouldn't have the freedom to look at the details they are interested in. So this is an interesting application for healthcare and NHS. Then another project is holoportation from Microsoft. So this is about telepresence, and here you can see real-time volumetric video reconstruction from 2 locations. You can see a multi-camera system, and participants here also use augmented reality headsets, so they can see each other, and their worlds are synchronized. And you can watch the video to hear more details. And here you can see the actual footage shot through HoloLens, so it's quite low latency, and it allows for this telepresence. And another example from Dimension is space opera. So this I think this is matching well the term imaginative uses in entertainment, and it includes a volumetric capture of a thinker integrated into a virtual environment. And I think it is a nice example of new forms of entertainment. So I recommend taking a look at those videos. And again, given that this capture is 3D, we have full control, and we can integrate it into any environment. So it brings a lot of control into the computer graphics world. And continuing with the application. So I mentioned training, telepresence, and entertainment, and you can see that those topics or applications are quite relevant, and here I included a couple of recent examples. So the first one is Project Starline from Google. So here you can see a really high quality real-time volumetric video system for telepresence. So it's trying to increase realism of video conferencing. And in the images below, you can see images from Microsoft Ignite from this year, and also the theme of the event was virtual worlds and interacting of people in those worlds. And here you can see examples of that. So there is a need for those virtual interactions. And applications as well include entertainment, and in particular events. So here I have also 3 nice examples. So this one is done by Nexus Studios, and it includes 3D players which are overlaid on top of stadium in a augmented reality experience. So volumetric video is a good way of capturing assets or volumetric people for such experiences. Another augmented reality use is in broadcast. So here you can see augmented reality renderings of the performer that were captured volumetrically at Dimension, and then they are overlaid on top of the camera feed of a tracked camera. And here is another AR experience that includes again our capture. This one was done for a fashion show, and the audience was able to preview the virtual model through their devices. So this is also a nice application of how to use volumetrically captured humans. But apart from entertainment, there is also there is a good application of volumetric video in research areas, and in particularly in dataset acquisition. So various research areas can benefit from such high quality datasets that a volumetric video can create. And examples include human detection, pose estimation, and given that the capture is reconstructed in 3D, this brings a possibility to randomize the content as a post process. So if you want to augment your data set and you want to create more data points, we can duplicate and create variations of the captured content. So it's quite scalable in terms of capture and in terms of post-processing. And you could also imagine volumetric video being used as a training data for RGB cameras, or infrared cameras, or we can simulate synthetic LiDAR data, because those often volumetric video systems, they capture performance in both visible and infrared spectrum. And you can imagine those data might be useful, for example, for sensing for autonomous vehicles, where those sensors are often used. And here are nice examples from CMU about their use of volumetric video data for creating datasets which they used for training various models. So here you can see their studio. It has plenty of use. This one particular studio has mixed camera configuration, so you can see more lower resolution cameras and then fewer higher resolution cameras. They have more than 500 views. And you can see that this system allows for capturing a lot of variations and a lot of data sets. And pretty much any action that can fit into the volume then can be captured. And this is in this video, this nice example how they used volumetric video data to improve performance of their hand key point detector. So with their initial model, which they trained beforehand, perhaps on synthetic data, they had the observation that if they run it on the views that were present in the training dataset, they can get good estimates, but it often fails for extreme camera angles, and they decided to incorporate volumetric video data into the training of the model to increase its robustness and accuracy. And here you can see failure cases of the initial model. But after they captured a more training dataset in a volumetric video system, they were able to create good ground truths. So here they were able to find those hand key points in views, because you can imagine that if for one view this is a difficult view, the system wasn't able to find the key points, but from other view, from different angle, it was able. And then if they took the good views and they triangulated the positions, they they suddenly had a really good ground truth, and then they were able to reproject that ground truth into those difficult views, and now they had another set of training samples which were of higher quality, and they were able to feed it back into the system. So they retrained with reprojected examples, and now you can see that in the next iteration the system was able to handle even those really difficult views. And here for comparison, this is the initial model which failed with those views. So this is a really nice example of how volumetric video data can produce really good ground truths for training model, and this can be repeated a couple of times, and this each time it improves the quality of the model. And here is the same idea applied for improving view robustness of facial key point detectors. So the same idea, the initial model performed well on in certain camera views. Those are views that were probably in their initial training dataset, but on other camera views it failed. And then after one iteration where they again created high quality ground truth data, they were able to feed it back into the model, and then on the next iteration the model performed much better for those views. And one other suggestion from those early papers is this one. Thus one could create a virtual world of a skilled surgeon performing an operation that students could revisit immersively, free to observe from anywhere in the operating room. And this is, in my opinion, yet to be done. There are still some challenges present that need to be addressed first, and they include capture, reconstruction, resolution, hardware setup, to name a few. And yeah, let's talk about early tests and what did the researchers manage to build and produce in those early works, and we will be able to compare it with present systems. So the one of the earliest stages, constructed in '95, was a 5-meter diameter geodesic dome, and it included 51 monochromatic cameras that were capturing at 60 frames per second, and the resolution was 512 times 512 pixels. And here are some of the results they managed to get from that stage. So here we can see a captured frame from one camera. Here we can see estimated depth. And here we can see also reconstruction from that camera view. So you could imagine it as taking image plane and reprojecting it into the space based on those estimated depth values. And if we take image plane and we project it into space, then we will have those severe discontinuities, but they can be isolated and they can be removed. And after we do this reprojection and remove those discontinuities, then we arrive at this reconstruction. But we can see that if we use just one camera view, we will have those occlusion artifacts, because that particular view couldn't see what is behind the character. But given that this is a multi-camera system, we can fill in those missing data from different views that were able to see that part of the scene. And here is the full 3D reconstruction, which is merged from the multiple views. Here is monochromatic texture applied in here, and here is also there are a couple of color cameras incorporated to the system, which are used for texturing. So here you can see the really initial results. And authors also demonstrated a technique that is commonly used today in that paper, and it is about inserting digital content into the capture. So Here you can see a virtual baseball being inserted into the captured performance, and we'll see that this is also a common operation in today productions. I will discuss a couple of them. And continuing about with a bit of history about capture stages. So in 1995, the recordings had to be digitized after the shoot, and digital capture was quite impractical. There were some systems, but they were really expensive and they weren't very scalable or flexible in terms of number of feeds. And with this view, with this system where they digitized the recordings after the shoot, the researchers were able to capture hours of content using any number of cameras. So they sidestepped the issue of direct digitization by digitizing it after the shoot, and that gave them flexibility to capture a lot of content. The same team built a newer setup with digital capture in 1998, and this system could capture 800 frames into memory and then had to write them down to disks. And here you can see a photo of that system. And in 2002 they managed to capture directly to hard disks, and in that case the recording time was limited only by available storage space on those capture machines, and this is pretty similar to the solutions that we have today. So you can see as the technology progressed, the volumetric video capture studio was also able to include higher quality cameras and perhaps more of them, and directly capture them digitally. And here is a nice slide I borrowed that includes present volumetric video capture systems from various research groups, and you can see that they share a lot of similarities, but each of them is unique in which is determined by the problem they are trying to solve, but there are a lot of similarities. And this borrowed slide also shows bandwidth of the captured data of various capture stages over the time, and also some predictions of what how the bandwidth is growing over time. So here we can see initial stages in 98. Then there is a USC light stage from 2011, which captured more data than CMU. Then there is MPI system and Microsoft system, which I will talk a lot throughout the presentation from Microsoft. And then there are two capture stages from Facebook. One is Maxi and one is Sociopticon, and you can see that the amount of capture data seems to grow exponentially. And since we are talking about volumetric video, which is really helpful with capturing humans and human performances, I think it's fair to compare it with the avatar-based approach and try to find similarities and differences in those two approaches, which are trying to solve the same problem, but those two approaches are attacking it from opposite ends. So in the avatar-based approach, an avatar is designed, modeled, textured, and animated with motion capture data. Perhaps then there is a hand keyframe animation on top of it. There are character effects. There are the character needs to be shaded, rendered, and this is the common workflow for visual effects or game pipelines. So in those workflows, we are trying to recreate reality from bottom up. And here you can see some really nice examples of those avatars. You can see that they can be quite realistic, but on the other hand, they require large teams of highly skilled artists to handcraft those features, and it's very tedious process. But the results are really good. On the other hand, free viewpoint video is recorded and processed. So its realism in real-time application is superior in my opinion. It requires less artist time, it's more scalable, but on the other hand it provides less control. So volumetric video system is capturing and reconstructing reality, as opposed to avatar based approach, which is trying to build it from scratch. But avatar based control gives us the full control and flexibility about the system, so we can make arbitrary design decisions. But if we are using volumetric video, this is reconstructing it's capturing the reality. So what we capture, that's what we get. So this might offer less artistic control when compared to avatar-based approaches. An ideal solution, I think, would be a hybrid approach, which would take advantages of both directions. And ideally, it would have the speed of capture and realism of volumetric video, but this would give artists the control to modify look and behavior as an avatar-based approach. And this area is pretty unexplored, it's quite new, and I think it's really exciting. And it requires designing novel workflows and tooling for that. And yeah, let's talk about some key properties or considerations of a free viewpoint video system. So not all properties are possible within a single solution, but those are important factors, and they often differentiate different categories of free viewpoint video or volumetric video systems. So the first one is scalability. So either in terms of the capture volume or visual quality or resolution and processing. So ideally the system is able to capture large stages, so that they are not limiting what action can be captured in them, and it can capture at needed visual quality and at the resolution, and also processing would be ideally scalable, so that we can capture a lot of content quickly. The system should be non-intrusive and natural, so it should just merely record the action without the need to modify it. So we shouldn't modify the lighting or look of the stage or performance for the ease of the capture. So it should be passive. It shouldn't interfere with the action, and shouldn't have specific requirements. It should be high fidelity. So the experience of the digitized event should be comparable to the real one, and this applies to all aspects of the event, including shape, appearance, motion, and so on. It should allow for unhindered immersion, so the digitized dynamic event should be viewable immersively from any viewpoint in the event space with few forbidden areas. So ideally the quality should be so good that we don't need to limit the viewing angles or distance from the capture that viewer can take, so he has a full freedom of picking their own desired viewing angles. And the system might allow either for tele or post experience. So the digitized event can be experienced either in real time or later on in an offline process, and this requirement often dictates the quality. So it's often a trade-off between quality and whether it's real-time or offline process. And the system should allow also for active participation. So the audience should have full control of time and space, ideally with the possibility to modify the content and appearance, making the viewer a participant. So it should be an interactive experience. And let's talk about dimension. This is a studio where I work, and which provided a sample dataset for this workshop, and I will talk about some of the works that that we do there. So Dimension is are experts in volumetric capture, digital humans, XR content, virtual production, location-based entertainment, and we also have a Polymotion stage. We do live events and VR game development. If you are interested, I recommend checking out careers. And I will show a couple of examples of some of those areas that we are working in. So here is a showreel from last year. So here you can see the quality of volumetric video captures that we can produce, and here are applications for. There was AR in broadcast. Here is location-based entertainment, and it includes a lot of digital humans because this is where the volumetric video shines most. And there are also we do a lot of game and VR development. Yeah, and I recommend watching the full showreel. I will also show nice video about virtual production, where we are also doing a lot of work. So this is a test shoot conducted with DNEG and others, and it includes a LED stage that was used for for getting good lighting of the actors and for doing in-camera VFX. And this is a similar stage like to the others you can find from other studios. So it has a bit of a real set that is blended seamlessly with the digital set, and this allows for efficient production of content with realistic lighting and look. So I recommend checking out this test. And let's talk to various approaches to free viewpoint video. So there are multiples. There are multiple ones, and each of them has its own pros and cons. So one of the main aspects that determines the end-to-end design and capabilities of any free viewpoint video system is a 3D scene representation, and it can be broadly categorized into model-based, depth-based, and image-based. And model-based 3D scene representation stands for often for polygons or voxels or point clouds. Depth-based stands for original captured views along with either estimated or captured depth map, and image-based are working with the captured views only. And in terms of acquisition for those three categories, model-based requires the fewest amount or relatively few number of cameras, but they need to span the full volume. So, for example, a dome surface, so that it allows for a wide navigation. Depth-based requires medium number of cameras. Is also number of cameras determines the navigation range. And image-based systems, they require a very dense sampling of the scene, and many cameras are really necessary to enable navigation, and this one requires the most of the cameras often. And in terms of reconstruction steps needed, in the model-based system the full reconstruction is happening, which is often compute intensive, it is error prone, and might struggle with difficult surfaces. But there are some aids, for example, using some prior knowledge of the capture scene can simplify the problem. Then in the depth-based system, it's using less reconstruction, so it's still doing depth, which is prone to the same errors like in the model-based, so textureless surfaces or visual ambiguities, but this one has much less processing than the full 3D pipeline. And in the image-based, there is hardly any reconstruction because we are mostly directly working with the captured views. Then in terms of coding or encoding the reconstructing medium for delivery, model-based has a moderate bitrate, can be well compressed and can be set to low at the cost of quality, but it can be low enough for delivering via web via networks streaming. So this is really a good property. In terms of depth-based, bitrate increases because we need to still store the original captured views along with depth data, and in terms of image-based, the bitrate is really high, especially if you have many views. And then in terms of rendering, the volumetric video experience captured by those three systems. In terms of so for the model-based system, rendering involves classic computer graphics. For depth-based, it's using often some sort of depth-based view interpolation, and in image-based systems, the rendering involves direct view interpolation of the capture views, and for example, light field rendering. And one of the important aspects of those systems is also free viewpoint video range. So this is the range that the viewer is able to move around the capture. So in the model-based, this is the widest, and it often allows for full navigation around the capture from all angles. In depth-based, this is medium, so this is determined by amount of cameras, but the viewpoint range is just in close proximity to the captured views. And in image-based, the navigation range is mostly limited because there's a high amount of cameras that are tightly packed together, so the system doesn't capture information from many views. And there is, so as we could see, there is this navigation flexibility versus processing complexity trade-off. And you can see that also those various systems there can be placed on this spectrum of image-based or geometry or model-based systems. So it's continuous systems. There are some extremes like the 3D mesh model or light fields or Lumigraph, but there are many systems that are somewhere in between, and we are going to talk about a couple of them. And generally, in the image-based part of the spectrum, the processing complexity is lower, so we don't need to do full 3D reconstruction. So it generally requires less processing, but it's data. There is more data to store, and the navigation viewpoint navigation range is smaller. While here in this case we have full navigation range at the cost of higher processing complexity, but also the data stored for delivery are much smaller. And image-based systems take advantage of very dense sampling, so they often involve many tightly packed cameras. It can directly interpolate views, and it sidesteps 3D reconstruction. But it requires a lot of cameras for wide navigation range and for minimum interpolation and occlusion artifacts. And yeah, many techniques are somewhere in between. So, for example, we could reproject captured frames based on an estimated depth map to allow for some viewpoint navigation, or we can use reconstructing meshes with view-dependent texture mapping for rendering. So those systems are somewhere in between. And the model or geometry-based representation is, for example, free viewpoint video captured in a DOM setup, and it includes representation includes meshes, point clouds, or voxels. And the drawback of this system is the need for accurate and 3D reconstruction of objects and scenes, which often can be tricky. And so those trade-offs, they involved number of cameras, compute, storage, and navigation range. And there is actually a nice relationship between the hardware setup of the geometry-based systems and image-based systems. So in geometry-based systems, we have a dome of cameras surrounding the scene, and in the image-based we have, for example, 2D array of cameras capturing the scene from one side. And in principle, the image-based and geometry or model-based approaches are very similar. Generally, we want a uniform camera distribution in both cases to have a uniform quality. And if we start with a geometry-based system, which can be a dome of cameras with wide baselines, so wide distances between cameras. If we add more cameras to the system and reduce distances between views, we increase the quality of synthesized novel viewpoints because we have more data to work with. In fact, if the density is high enough, the need for correspondences is eliminated, allowing for direct interpolation of images using algorithms like the Lumigraph or light field rendering. So this is, however, often impractical due to the number of views required, and especially for dynamic scenes. So if we were adding more and more cameras to the geometry-based system, we would be basically approaching the image-based systems, which have a lot of cameras, and given the higher density, we don't need to do the 3D reconstruction, and we can get away with directly interpolating images. And let's talk about products and studios that are involved in volumetric video capture. So there are actually a couple of them using different types of technology. They are spread in many countries. And if you want to get a good overview of various systems and locations, I recommend checking out this infographic, which is produced by Arcturus, and this one is the most recent. It shows it's pretty good overview of the current situation. And a good overview as well is on this link, where you can see various studios and systems and some of the information about them as well. And I included a couple of them in this presentation as well. And generally those studios or those products have different requirements. They can produce different quality at a different cost and at a different processing time. And I've split them into 3 categories, but this differentiation is just based on my limited insight, and I really apologize if I misclassified some products. So in the first category, I placed high-end capture systems, and by high-end I mean that they generally have long processing time. They are compute resources intensive, and they often involve many high-resolution cameras. So I will click through them to get you general idea. And the last 2 ones are Dimension and Avatar Dimension, which is our partner studios, and I already covered some of the work from Dimension. So Canon has volumetric video stage. There is also a stage from Intel Studios, which is closed in the meantime, so it no longer exists, but I think their technology and approach is still quite relevant. So they have pretty high volume. Then I picked this example from Infinity Realities because it shows really high quality capture that can be reconstructed from their system. You can also see really nice material properties. And there is 4D views, which are also doing very impressive work. There is 8i, and there are holograms, and also a VoluCap in Germany, and there is also a meta stage. So those systems tend to be higher quality, but at a higher cost and longer processing time in many cases. Then there are mid-end systems, which often take advantages of depth sensors. They have generally shorter or sometimes even real-time processing, and they capture either one viewpoint, for example, just one side of the character, or multiple ones are merged using multiple sensors. And some of the systems can estimate skeletons as well. So I will click through a couple of them. So one is this EV, where you can see they're using the common depth sensors hardware. This is in this presentation is from a Capture product, and here is a nice skeleton estimation that you can do using multiple camera views. And I wanted to include it to show that those systems are often robust and they can produce really good skeletons, which are often helpful during the volumetric video creation or production. Then there is holocap system, and Evercoast, and Mantis Vision is also doing very cool stuff, and there is also DevKit. So couple of products and studios from this end. And then there is also this third category, which includes research projects, open source projects, and low-cost systems. So these are not productized yet, but they have very good quality, or they can manage to create a decent quality at much lower cost. So I will go through them. So the first one is the Relitables, which is very impressive free viewpoint video system done at Google. So I will compare it often with the Microsoft stack. So this is really impressive work that's pushed the quality bar of volumetric video. This is holoportation, which I already showed from Microsoft, and this is a longer presentation. So if you want to hear more about their pipeline, then this video is a really nice overview. Then there is Fusion 4D, which is a real-time capture system, which the real-time aspect of it is really impressive. You can also see the quality is quite good, but there are some artifacts which is tricky to solve in real time, but the quality is pretty good. Then there is a similar
we present Motion to Fusion, a state-of-the-art
motion to fusion system. So I recommend taking a closer look at those systems. And there is also a project Splinter, which is interesting. Research group doing a lot of relevant research in these fields, and many systems are real-time. They include just maybe one viewpoint, and I will touch about some of them in the presentation as well. Then there are also various datasets if you want to experiment with some techniques and want to use some ready data. Then there are a couple of options to pick from. Then there is also this open source volumetric capture system, so it can work with various sensors, and this is also good if you want to experiment with DII solutions on your own. There is also this nice article at volumetricvideo.com which shows how to experiment with volumetric video without owning any hardware. So they use a data set and they process it through various systems. So they use Blender for visualization. They use I'm not sure, but they use something for meshing. They use Open3D also for registering different views and the texture mapping in MeshLab. So it's possible to play around with those data without owning any hardware or volumetric stage studio. So this is nice tutorial, and this is also really impressive work showing how to capture a volumetric video system using low-cost cameras. So in this case, I think they use Raspberry Pi cameras, and their stage looks like this one. So they show how to approach some of the problems using low-cost approach. So those things are quite relevant and quite interesting as well. And then let's talk about tools. So if we manage to capture our content, how do we work with it? There is a lot of room for making new tools, especially from technical directors, and that's thanks to the fact that visual effects applications and standards are often used. So this volumetric video thinking is a natural extension to VFX and tools and workflow. So it's using same tools. In the second part of the workshop, which will be hands-on in Houdini, you will see that many techniques are used that would be used with any other 3D data. And those tools, they range from custom computer vision tools to geometry processing tools and to off-the-shelf packages like Blender Unity or Unreal Engine 4, and then to Houdini and Nuke. So Nuke for image processing and Houdini for geometric processing or anything really. And there is a need for pipeline and tooling for helping with managing assets, moving stuff around, optimizing for operational cost, minimizing artists' room for errors and their performance. And there are a couple of toolsets there, so they include HoloEdit and Sense XR Studio. So those systems are directly tailored for the volumetric video data, and they really help with some of the common tasks associated with processing volumetric video systems, and they often have also timelines, and they allow for combining or creating rich experiences by combining multiple captures and maybe doing some animation overrides and doing further processing. There is also interesting R&D project from Foundry, which is a company behind Nuke, and it's called Volumetric, and here they discuss their approach to volumetric video processing in Nuke. So they pose it as a compositing or image processing problem, and Nuke has a lot of those tools for image processing, computer vision, and they have also 3D systems, so it can be a nice environment for producing such content. I recommend reading through it. And in terms of playback volumetric video, so current situation requires either proprietary game engine, if this is where the content is delivered to, or it requires web plugins, and by plugins I mean JavaScript libraries that can decode the volumetric video, or they require standalone apps, for example for desktop. And there is also interesting application, AtomView, which now seems to be owned by Sony, but in that application they also showed example of playing back volumetric video content. And in the next few chapters I will go over the whole production pipeline, so starting from acquisition to processing and post-processing, and this is intended to give a good overview of the whole pipeline. So this is more focused on breadth rather than depth, but hopefully it will give a general idea of the issues and steps needed for capturing and producing volumetric video content. So let's get started with acquisition or capture. So most free viewpoint video acquisition systems use multiple cameras to capture real-world scenery, and these systems can often be combined with infrared cameras or depth cameras or structured light in order to capture the scene geometry. And therefore there is this classical trade-off to consider between costs for equipment, cameras, processors, and quality, which refers to navigation range, quality of virtual views, and so on. And when speaking about cameras placement, we can speak of their topology, and it can be broadly categorized into two categories. So one is outward, which includes a group of cameras packed tightly together at the center of the captured volume, and they are capturing everything outside. And those systems or cameras, they include those two research projects, for example, but there is also commodity hardware like Insta360 or Y or GoPro cameras. And here you can see camera system intended for capturing light field in motion. And this is also similar system or project called Welcome to Life Field, again from Google, which is capturing a really high quality light field of a static scene, and it allows for a really faithful representation or 6 degrees of freedom experience, especially in VR. So I recommend taking a look at this project, and ideally at the final experience, which is I think available at Steam VR store. And there is also inward camera topology, which includes a studio or might be also a stadium setup, which uses often machine vision or DSLR cameras, or in some cases even high-end cinema cameras. So you can see multiple cameras pointing at the stage, or like in this example from for capturing ballot time. And a really important aspect of any multi-camera system is synchronization, which is crucial to correctly virtualize time-varying events, because stereo algorithms, so the algorithms that are reconstructing, estimating depth or reconstructing geometry, they assume that images from different views correspond to static scenes, so they all capture the same time instant. And synchronization is crucial for satisfying this requirement. And there are generally two steps for synchronized multi-camera capture. So first one is aligning frame capture of all cameras. This can be achieved with Genlock or tri-level sync. And then there is a second synchronization system which allows for time synchronization of all different cameras. So all different cameras, they can start recording and maybe with a couple of offsets, and this if it's using timecode or etc, this can help to bring all those camera feeds into the same time. And in terms of cameras and capture systems, so there are various options. They range from off-the-shelf to custom built, and one to include a couple of examples. One of them is IOI, which provides both cameras and capture system. So they have a product specifically for volumetric capture, so I recommend taking a look at their offering. And there is also AVA capture, which is open source project from EA Seed division, and this is a distributed camera capture system. This is made to work with Xamia cameras, and those cameras are these are machine vision cameras that are often used in such volumetric video system. And after we have our stage with well synchronized cameras, then before we can do any reconstruction, really we need to calibrate them, and calibration involves estimating a couple of camera parameters, and they can be split into two areas, so or two categories. So one is intrinsic parameters and one is extrinsic parameters. And intrinsic parameters, they include focal length, principal point offset, aspect ratio or skew. So these are parameters that model that characterize a model camera that is trying to estimate the real camera. And there are also extrinsic parameters of that model camera, which includes its position and orientation in some coordinate system. We also need to find out lens distortion parameters. So often lenses, they distort lines. So straight lines in the real scene, they often appear to be distorted in the captured frames, especially towards the borders of the frame. And this calibration step is crucial for all subsequent steps. So it's really critical to get it right, because if this calibration step, if there are some errors in it, they will propagate through the rest of the whole processing pipeline. And next example of how to approach calibration is a Microsoft system that uses Octoleaf object, which needs to be moved around the stage, and it calibrates both intrinsics and extrinsics. And here is the picture. So it is a known geometry with with checkerboard patterns, that there is also encoded information about them, and so if multiple views can see the same pattern, then the relative camera positions can be derived from that, and then a bundle adjustment can optimize all the parameters and minimize for the reprojection errors. And in this presentation I will be focusing mostly on inward cameras topology. So it is a dome of cameras or similar setup where are many cameras pointing inwards. And in some of the systems I will mention as well use both visible spectrum cameras and infrared spectrum cameras. And let's talk about specs of a Capture Studio that we have at the dimension. So this is the source. So if you here are answers to some frequently asked questions. So I recommend taking a look to get a general sense of what does the capture process look like and what are some of the hardware present at the stage. So we are often shooting at 2K, which is 4 megapixel frames, or 4K, which stands for 12 megapixel frames, at either 30 or 60 FPS, and at the various bit depths we have both visible and infrared spectrum cameras, and we also have infrared projectors. And the motivation behind infrared projectors is that often surfaces don't have any texture, and therefore they would be challenging for depth estimation, and that would affect all the further steps of the reconstruction pipeline. And therefore, if we can use infrared projectors to project some random pattern on the surface, and given that it's happening in infrared spectrum, it doesn't affect the visible texture, but it helps with the reconstruction because we are using infrared cameras as well. So if there was some flat surface that would be hard to reconstruct in visible spectrum, then in infrared spectrum it will have some sort of texture on it, which is projected by those projectors, and this will help with reconstruction. And here we can see two examples. So one is from Google Serializatables, where they have this kind of pattern, and on the right is Microsoft system, which is using this sort of pattern. And before the actual shoot, we usually capture test samples to see how the clothing looks like in the infrared spectrum or visible spectrum, to see if there are any issues with perhaps aliasing or reconstruction. So before capturing a lot of content, we do those look tests to make sure that the material reconstructs well. And for example, at 2K resolution, we have 10 gigabytes per second bandwidth, and we can capture around an hour per day. And we have volume of around 3 meters in diameter, but we have multiple stages, and often those camera configurations or on diameter, they are configurable, and they are quite flexible, so they can be adjusted for specific project needs. And this is nice graphic from the Reliatables paper, which is showing the difference of geometric reconstruction of 2K and 4K cameras. So we can see with 2K cameras we can get decent geometry reconstruction, but if we increase the resolution to 4K, then we can capture much higher frequencies in geometry and in texture as well. So it helps with the quality of the capture using better cameras. And just to give you an example of what the captured views look like. So we already saw at the beginning at the CMUs their capture stage that it's similar, so many views, and those views they can be they can have like different aspect ratios. So depending on the scene, they can be also in the landscape or portrait orientation, whatever works to maximize the amount of pixels that can capture the scene. And then in terms of studio background, so often green screen or blue screen is used as a background, and this aids with segmentation or with keying out the foreground. But there are also like other options. So VoluCap uses white background, and they have on top of it controllable lighting, which allows for arbitrarily lit background, and yeah, they can do like different lighting scenarios. And Facebook's Sociopticon has also a white background. So this is a VoluCap Studio, and here is also Sociopticon from Facebook. So you can see those black circles, those are camera lenses, and those smaller things, which there are many more of them. These are actually spatial microphones. So in that studio they are also capturing really high quality audio of the capture, and they are doing it really interesting reconstruction of that as well. And in terms of view sampling density, so the capture space could be densely sampled in a studio environment, or it could be more sparsely sampled outdoor or even stadium environment, like this Intel's TrueView technology, which I think is former Replace 3D technology. So here you can see yes, stadium with many cameras, but given the big size, the baselines between them are really large. And here is a nice example of what sort of experience Intel can create with this system. So here you can see they can do those reconstruction quickly, and they can replay the scene and show like interesting angles. And they have quite good quality. Yeah, given their setup and processing speed. So this is an interesting application in sports. And in the image-based domain, there is often a dense one-dimensional or two-dimensional array of cameras, like this one array developed at Stanford. And I would recommend watching this presentation to get more information about volumetric capture, Facebook's avatars, and recording sound, and some challenges like reconstructing hair. So I really recommend watching this presentation done by Yasser Sheikh at the University of Washington Reality Lab. And author of this presentation, he was also present in the same lab that Takeo Kanadi and others were doing their research into virtualized reality. So all those researchers, they're often related, and they collaborated on similar projects. And this is a really nice overview of the topic. And I borrowed many slides from that presentation. And then in terms of camera sampling, so if we have a given amount of pixels for a given scene, so we can have multiple configurations. For example, we can have many more cheaper cameras which have also lower resolution or smaller sensors, or we can have fewer cameras which have better sensors at higher resolution but at higher cost. So given the same budget, we have those two extremes, and this one helps with visibility. So we have many views which are allowing for good visibility of all the parts of the scene. And this one system allows for really high resolution and detailed geometry and texture capture. So there are trade-offs between those two configurations. And so now, after we covered the capture process, let's continue with the processing pipeline. So this nice video, which is accompanying the research done by Microsoft, is showing a nice high-level overview of the steps needed.
We start by capturing performances with 106 synchronized RGB and infrared cameras on a calibrated green screen stage. We subtract the background to compute silhouettes, then schedule the data for processing. The first step generates a 3D point cloud starting with stereo depth maps from RGB and IR pairs. Points from these depth maps are merged and refined locally. Then the cloud is refined globally using a multi-view stereo algorithm. This result has over 2.7 million points with normals per frame. We're viewing tens of thousands of points in this scene. The next stage creates a watertight mesh per frame. We modify screen Poisson surface reconstruction to produce meshes constrained by the silhouettes. These meshes typically have topological artifacts and spurious components. To clean them up, we apply topological denoising and island removal. This result has over 1 million triangles per frame. Next, we determine which areas contain perceptually important details such as hands or faces. We preserve the quality of geometry and texture in these areas when we decimate the mesh to its target density. This example is reduced to 20,000 triangles per frame. We then establish temporal coherence by choosing mesh keyframes and deforming them to fit ranges of the performance. This coherence is critical for compressing mesh motion and textures. This example was split into 4 subsequences. The final step is to unwrap the meshes, generate a texture atlas, then compress and encode the data in a single streamable MPEG file at our target bitrate. This example is running at 12 megabits per second. Let's take a look at some example captures from our system.
So you could see in the video some of the things that we could also see at the beginning of the presentation of the sample capture. So there is higher polygon density on the face. There is also higher texel density. There are also there are sequences of consistent topologies, but there are changes on the extreme capture changes as well. And I will go over those steps in the following slides. So each of those steps is a really broad research area, and those are the stages. So we start with cameras, then we pre-process images to for example correct lens distortions and match exposures of the cameras and so on. We also do subject segmentation to key out the foreground from background, and those informations can be used for generating depth maps using multiple modalities. And if we generate depth maps from those various stereo pairs, they can be merged together, and we can arrive at the point cloud using a multimodal, multi-view stereo system. And from that point cloud, we can then mesh it. But this mesh often contains a lot of artifacts and some topological noise, so we need to improve that. And after that, we can decimate geometry while keeping higher density at face. We can also reproject texture. We can track the mesh, so we can track the similar. We can track sequences of similar frames in terms of topology, and then after texture projection, we have the final asset, which can be, for example, encoded into a single MP4 container. And those processing steps, they are pretty similar in other systems as well. So here is a figure from Volucap's system, and here is setup from Intel's. So you can see there the general processing pipeline is very similar for all of them. So you can see in here at Intel they first did calibration, image processing, 3D reconstruction. They do further point cloud processing and post-production and distribution. And it's yes, similar here as well as Volucap. And Google's Relay tables, they have also similar pipelines. So input cameras. We can see they have both infrared and color cameras as well. They have then they calculate those depth maps from a multi-view stereo, and it's active, meaning that they have those infrared projectors in the system as well. And they do also multi-view semantic segmentation in 2D to aid with isolating the foreground and also labeling different parts of the mesh. And then they arrive at point cloud and they do post-on reconstruction, which is often done to convert a point cloud to measure point cloud. And in terms of geometry types, free viewpoint video techniques can be broadly categorized according to whether they reconstruct a new surface at each frame, or they deform a canonical or pre-computed geometry model, for example body mesh, to fit each frame, or they use some sort of hybrid combination of per-frame reconstruction and inter-frame tracking. So we could see in the Microsoft system, after they do after they mesh their point cloud and they do cleanup and decimate the geometry, then they have a unique geometry for each frame, but then they do this inter-frame tracking to have some consistency in sequences of similar frames. And this Microsoft and Google's technique is also model free, which means it can generalize to any capture scene. It doesn't make any assumptions, or it doesn't use any priors of the captured content. But other systems, they might assume a human capture, and then they use some models which simplify reconstruction, but they do some assumptions. And in terms of doing this interframe tracking, so the motivation behind it is that reusing the same keyframe mesh connectivity over several consecutive frames, or even the whole sequence if it allows for that, can really improve robustness and encoding efficiency. So this is a mostly compression consideration. On the other hand, allowing for dynamic mesh connectivity changes offers a greater flexibility in capturing general scenes, for example with free flowing clothing or interacting objects. So we can see we can't always place this constraint of having a consistent topology if there are big changes in the scene. And this is by allowing for those topology changes, we can really capture general content, and the system is really flexible. And techniques, so those model-based techniques can use prior models of scene geometry, which help with mesh consistency, or they provide additional control above it. They also help with visual ambiguities, motion editing, but are limited by the priors. So if some system is assuming a human body, they might struggle with capturing animals or props, or dynamic lighting, or loose hair, or clothing. So there are some limitations with those approaches. And Microsoft's approach uses hybrid methods, so dynamic mesh connectivity, but with interframe tracking. And geometry changes happen when it's necessary. And to talk about the model-based approaches, or the systems that use some templates, geometries, or prior models, they often include a skeleton or scanned mesh or statistical models, like example STAR from MPI. So MPI did a lot of work in this area, so they have a lot of those statistical parametric models of humans. So STAR is one of the recent ones. There is also a Simple and Simple X and Dimple, a couple of more. So they are doing really interesting work in that area. And while this simplifies the problem, it reduces the generality and flexibility of the system. And here is on this figure we can see just a couple of research projects, and The top row uses a model or prior free approach, so this generalizes well. It also includes the Microsoft stack, and the bottom row uses priors or is model based, which simplifies the reconstruction problem, but at the cost of generality. And let's continue with image preprocessing step. So one of the image preprocessing steps is image segmentation, which helps with reconstruction shape quality later on, and also speeding up the rest of the pipeline. And some other steps that are commonly used, like shown in this slide from Intel's presentation, they include denoising, vignette correction, gain normalization, debayering, white balance, color correction, or fixing frame tears if they happen. And after image processing, there is this point generation step, and first the point clouds per frame is generated by estimating depths from stereo pairs and silhouettes, and multiple depths are then merged together using a multimodal multiview stereo algorithm. So I'll elaborate on it. And those multiple modalities that are used, the reason behind that is like here stated in the free point video paper. So our key insight is that no sensing modality can resolve every challenge, but that each modality is best suited to resolve different challenges. So if we can use, for example, those three inputs, so one is shape from silhouettes, which is visual hull constructed from those segmented views of cameras, and we can do multi-view stereo on RGB cameras and multi-view stereo on infrared cameras. We can bring all those information, and ideally we will be able to reconstruct the whole capture. And to continue on that topic of multiple modalities, so here are examples, and we can make a couple of observations from those data. So on the last column, here is the final result, and as we see from color coding, it's created by combining all those different inputs. So the first column on the left is shape from silhouettes input. Then in the middle is a multi-view stereo from RGB cameras, and here the blue one column is multi-view stereo from infrared cameras. And something we can notice is that the golf club is resolved well in shape from silhouettes input. So this one is the highest quality when compared to other inputs. And for example, in infrared spectrum, hair and shoes are not very visible, but they are well resolved in RGB spectrum, and the full reconstruction combines the best of each modality. So if we did surface reconstruction for those individual modalities, each of them would have issues at some areas, but if we combine all of them, we get the best results and the most robust. And let's talk about shape from silhouette or visual hull reconstruction. So the principle of this technique is that first a subject is segmented in each camera view, like we saw in the image processing step. And here we have examples. So we have those alpha masks of the subject. Then the 3D volume of the object of interest, or more precisely its convex hull, can be reconstructed using volume carving. So you can imagine if we have here our volume that we want to reconstruct, and if we carve away the empty areas based on those 2D segmentations, we can arrive at the silhouette in the middle, which is intersection of those all volumes. But it's not perfect reconstruction of the scene. It is its convex hull, and it's caused by the fact that we have a limited number of views, and therefore, even though if our object can be like this ellipse, given, for example, just 3 camera views, the best we can do is we can arrive at this convex hull, which is guaranteed to encapsulate the subject, but there might be still some empty space on those edges. And yet this is sensitive to segmentation quality, so it's good to get that right. And given that it is just convex hull, it cannot represent concavities such as self-occlusions or eye sockets or mouth openings. And here is a nice explanation. I recommend watching to get more information about it.
We're now looking at our Rubik's Cube from above with a camera at the side. So here's my camera, right, and here's my Rubik's Cube. Most cameras are not orthographic, which means that they don't look in parallel to the scene, they look at an angle. They're conical shape. The projection matrices are conical. So this actually sort of squishes all of this scene in here like this, okay? Which actually means that the cube is slightly distorted. This is why you get things like barrel distortion. Well, it's one of the reasons you do. So the problem is that this camera sees an image that looks like that, okay? A square box inside some background, right? So it carves away, but it can't carve away parallel to these edges because it can't see parallel to the edges. So actually it carves away like this. So not only do we not know what's in here, but we also don't know what's here and what's here. Now if I bring in another camera, my paper's getting quite thick, quite full of stuff, so here's another camera here. This is going to come in like this, and so now my object is, well, and sort of this bit, okay, so now my object is that shape, which still doesn't bear any resemblance to our cube at all. In the literature, this is called the photo hull.
So I recommend watching this video for a good overview, and here is also a relevant research paper which describes the technique. And the next step can be point cloud processing. So it can include cleaning, segmentation, completion tracking, retargeting, or pose estimation. And after we have point clouds, then we need to do meshing and texturing later on. So often Poisson surface reconstruction is used, and in the example of the Microsoft approach, they used a screen Poisson surface reconstruction, which is clipped by the shape from silhouettes. So the reason behind doing that is that given our input point clouds, if we do surface reconstruction, we can get those errors, like even though we can see there is an opening in the hand, it gets closed. The skateboard shape is much thicker, and there are also those connections between different objects. But if we clip that Poisson's field by the shape from silhouette, then if we do the meshing, that we can get rid of all those issues, like in this case, and this gives pretty good results. And after this surface reconstruction step, we often have a lot of this topological noise, which can include all those small bridges or handles in the geometry, and we need to do topology denoising to increase the quality of further mesh processing, for example simplification, unwrapping, and it is also needed for a robust characterization of surface genus, which is later used for keyframe selection heuristics. And in order to have a good surface genus characterization, we need to remove, get rid of all those small handles and tunnels. And let's dive a little bit into the surface genus and what it means. So let's digress for a moment. And genus can be intuitively understood as a number of handles or holes in the geometry. And to give a couple of examples, for example, sphere or cylinder or box, they are genus 0 because they have no holes in their topology. For torus or coffee cup, they are genus 1 because there is one hole or one handle, and you can see that from topology point of view, torus and a coffee cup, they are pretty much the same object in terms of topology. And then we can continue, so we can have genus 2 surfaces, genus 3 surfaces, and so on. And yeah, let's do a quick quiz time. So those 4 objects, they are test objects present in Houdini. And yeah, let's try to think about what genus they might represent. And yeah, to answer those cases, this pig head is genus 0, and I'm assuming that the mouth isn't connected here. So you can imagine this could be well wrapped onto a sphere, and it can have the same topology as a sphere because there are no holes in it, and I'm assuming that the eyes are closed as well. In the case of teapot, this is genus 1 because we can see one hole or one handle in the object. I'm again assuming that this is all it's closed orientable surface, so it's all closed. This squab geometry is also genus 0 because there are nothing is connected. There are no like holes, and rubber toy is also genus 0. But that was just a warm-up. Let's continue with more interesting examples. So this one or this one shape, and it gets even more interesting if we try to think of surface genus of open surfaces, which might not be orientable, and it is possible also to determine genus of those surfaces, but it gets more tricky, but more interesting as well. And I will leave the answers as a homework for the curious ones, and you can find them in the links below images. So I really recommend taking a look at those links if you're interested. And there is also this elegant Euler Poincaré formula, which can be used to determine a surface genus of orientable closed surfaces. And if the genus is G, and E is number of edges, V is number of vertices, and F is number of faces, then we can determine genus by this formula. So it stands for E minus V minus F plus 2, and dividing it all by 2. This will give us the number of the surface genus, and I recommend trying it out, for example, in Houdini. So I put here a snippet of code that you can copy paste, and it will give you surface genus of a closed surface, and you can run this in detail mode, and you will have integer genus attribute, which will show you what genus the surface is. And then going back to the reconstruction pipeline of volumetric video, then let's talk about importance detection. And we could already see at multiple places that in many cases we allocate more polygons to face or hands or the part of the body that we care about, and there are multiple motivations behind that. So here are examples of the visual quality if we use the same polygon and texel density for face as the rest of the body. And here is the example if we allocate more polygons and more texels to the face area. We can see that the perceived quality increases, but those two examples, they have the same polygon and pixel budgets, so we just changed proportions. We distributed more information to those areas because humans, we are more critical to judging quality based on those parts of the body. And here is example from the relatables from Google. Here you can see what the texture atlas would look like for a regular capture, and here is texture atlas that includes this importance detection, which scales up the UV island of polygons that are on a face or on a head. And the next step in processing pipeline is texturing. And this texturing requires carefully registering images to geometry and blending of samples from different images, and this is really dependent on the calibration step at the beginning, like other steps as well. And in the case of Microsoft's paper, camera contributions to the texture are weighted by the underlying triangle normal direction, which means that it prioritizes good camera views without distortions, and view dependent textures could further increase realism, but currently it is impractical for web streaming. And to elaborate on this normal weighted blending, the idea is that, for example, if you are considering my webcam camera view and palm of the hand, if I want to texture it, then this camera view would be well suited for reprojecting the texture. But for example, if we used a triangle that is oriented like this, in this direction, that we can see that the texture would not be really good. It would be stretched and it wouldn't contribute with the best information. So instead we pick a different camera that is aligned with the normal of the surface. And next step in the pipeline is temporal mesh processing or mesh tracking. And at this point we have a textured high-resolution mesh with different connectivity at every frame. And in the Microsoft system, they automatically select suitable keyframes and track them over sequences of frames to produce temporally coherent subsequences. So in the pipeline, they are trying to group frames of similar geometry topologies together, and then they can track one consistent topology over them. But when the change gets too extreme, then they switch to a new topology and track that further. And this keyframe selection steps in Microsoft's case, they use a couple of heuristics. So they compare surface areas of different meshes at the different frames. They compare surface genus of different frames, and based on those values, they can arrive at a good heuristic which tells if the frames are similar and they are suitable for tracking, or they are too different and we need to insert a new topology. And this temporal mesh tracking really helps with geometry and texture compression. So it tries to, in case of texture compression, it tries to minimize texture changes between multiple frames. So if we I will show it in the next video, but if we do mesh tracking, then UV islands, they don't jump around that much in the UV space, and that is really critical for using video compression on the texture to optimize bandwidth. And this temporal mesh tracking has certain limits, and it all depends on scene dynamics. So for example, static scenes can be tracked for longer periods, but longer lots of moment will require more keyframes on the other hand. And here this video shows a nice example of to geometry tracking. And here is the input, which is sequence of unstructured meshes, and it means that each geometry has unique topology. And here is the keyframe meshes. So this is based on the high quality free viewpoint video paper from Microsoft, and here is their further work which improved on their technique, which does localized topology changes to the geometry. And the topology changes will be visualized by red frames. So here we can see if the geometry change is big, then there is a new topology inserted into the sequence. But in this case, we are inserting only local polygons only in the localized area. And here we can see impact on the UV atlas or the texture parameterization of the mesh. So in the input we have unstructured meshes and the UV layout changes on each frame. In the middle we get changes, we get global changes, and on the right we got only local geometry changes. And here we can see impact on the bandwidth after compression of both geometry and texture compression. So those three examples, they have very similar visual quality, but to achieve that quality, the first example requires 8 megabits per second. Okay, so texture and this amount of triangles per frame, and if we do this global keyframe, then it reduced the bandwidth, and if we do the localize, that further reduces the bandwidth for both geometry and texture, and they are both much easier to compress. And this video also shows example of the complex topology. So in order for a volumetric video system to be general, there is a requirement for topology changes. So if we consider this capture, so the subject is taking off a shirt and taking on a jacket, this would be really tricky to track with the consistent topology. But if we can vary the topology, then we can really capture this arbitrary surface. And oh yeah, let's talk about impact of texture compression of this topology tracking on the texture compression. So here we have two examples. In top row we have untracked geometry, and we can see that the resulting parameterization to the parameterization shows that here is a part of the surface that they're interested in. On the next frame it moved to this side, and in the next frame it moved here. And on the bottom one we have this geometry tracking, and here we are showing the one sequence of the same topology, and we can see that the one patch of a surface, it stays at the same location. And if we then compress those two streams with the standard video compression like H.264 or H.265, we can see the impact of the visual quality. So those two encodes have the same bitrate, the same bandwidth, but given that we can compress the bottom row significantly, we can use the same bandwidth or same bitrate for much higher quality. So it has really big implications on the compression and on the texture quality of the resulting video which is then delivered. And another aspect to consider is relightability. So some systems, for example the relightables from Google, can capture high frequency photometric surface normal maps and estimate shading textures like albedo, roughness and ambient occlusion with the help of a light stage. So this is in contrast with Microsoft's approach, which has lighting baked in, and the normals can be estimated from the reconstructed geometry only. So the relightable setups, they have a light stage, so they have controllable lighting, and thanks to that they are able to capture really good normal maps along with other textures, and this helps with relightability. And here we can see example. So the capture stage of the relightables, or the light stage, it illuminates the capture at high speed with two alternating illumination patterns, and that can be used. This illumination pattern can be used to derive normal maps, and with help of that, they can also derive roughness and AO and possibly other maps. And here is also albedo, and this is the resulting capture. And to show the impact of captured photometric normal maps on the perceived visual quality, so this is the same idea as is present in the game development for a long time. So geometry, in order to capture high frequency details in geometry, would really have to use higher poly count, and it still it could be better in this case of 100k triangles. But if we use the same polygon count, but the photometric normal maps, so this one stores the apparent geometry high frequency details in the texture, we can get this really good visual quality even at lowest poly count, and this is still better than the 100k of the capture without the photometric normal maps. And even if we increase the geometry poly count, we are improving the silhouette of the capture with normal maps, but the quality improvement is not that visible, given that even the 5K looks pretty good. And there is also a comparison of Microsoft's and Google's free viewpoint video system. So this is from Google's paper, but I think it's a pretty fair comparison. So here in top row there is work from Collett et al., research from Microsoft, and those are the results that their system produces. And here is here are results from Google's, which is Guo et al. Research team, and these are the results they can produce. And here is also their result with texture. And yeah, some observation to be made is that their reconstruction exhibits more geometric detail due to higher resolution depth cameras, but I think mostly due to the photometric stereo normals estimation. And the last couple of slides I talked mostly about model-based techniques, but there are still relevant image-based techniques which are also producing decent results, and they are interesting as well. So if we have two or more views of a scene available, then we can estimate a disparity between the two. So we can estimate disparity or depth map, and from that we can derive 3D depth of the scene using those correspondences for depth estimation. And some image-based techniques reproject the picture into the space based on the estimated depth value and do some in-painting to occluded areas. And this, however, offers only a limited range of viewpoints. And this has the similar limitation like the model-based approaches, so it suffers from errors in textureless or ambiguous surfaces. And some approaches combine color cameras with specific depth sensors that directly capture scene depth, for example, time of flight, or structured light sensors like Kinect. And those occlusion artifacts discussed can be addressed by using multiple camera views with estimated depths. And for example, this system is called multi-view video plus depth. And this helps with those occlusion artifacts, and the idea is similar like in the model based, that if there are occluded areas in one camera view, this information can be seen in different views. However, this system leads to a huge amount of redundant data, so new views are contributing with only little new information, and the majority is visible in other views as well. So to address that, there is an alternative representation known as layered depth video. And in this case, image information is stored in different layers that are extracted from the original views by projecting the views onto each other and eliminating duplicate content. So we can imagine that if we get occlusion artifacts from one camera view, then in a different camera view we can store only that missing information. So that helps with the data redundancy. And here is also video showing very important research. It's a couple of years old, but it has very interesting results, and it shows this technique. So they have this sparse sampling of the scene, and they are able to reconstruct novel news from this proximity to the captured cameras. So let's take a look at their. I will show a fragment of the video, and then you can take a look at the whole video afterwards.
Rendering. In this paper, we describe our approach for capturing, representing, and rendering dynamic scenes from multiple points of view. Here we show a real-time rendering result. Note that the virtual viewpoints are interactively chosen at display time. Our goal is to allow the user to interactively change the virtual camera position while viewing the video. One way to achieve this goal would be to film the scene from many different viewpoints. The user could then select between the cameras. However, a large number of cameras would be needed to reduce jumping artifacts as the user changes viewpoint. The jumping effect is even more noticeable with a smaller number of cameras. Our approach is to render high-quality virtual viewpoints by smoothly interpolating between a small number of captured videos. Our rendering system consists of offline and online components. The video capture and processing are done offline. Video processor system
So yeah, in this picture we can see their capture setup, and they first do the calibration to get the relative poses of the cameras, and based on depth they can do depth estimation, and they can using the depth information they can do some clever view interpolation between different views, and they get quite nice results. So here we can see example of the occlusion artifacts, and then the filled in information from a different view. And then the next step in this high-level volumetric video production pipeline is coding and transmission. So after all those steps, we have captured our data, we have reconstructed it, and we have in case of model-based systems, we have a sequence of geometry meshes and textures, and ideally with some consistency in them. And then the next step is to encode those data so that they can be delivered, and they can be compressed and efficiently delivered to the audiences. And I think in general that free viewpoint video encoding of model-based systems is usually similar to this workflow as shown in the volumetric diagram. And so after the volumetric video reconstruction system provides us with free outputs, which is mesh or sequence of meshes. Then there is a texture map, and then there is audio. So I haven't talked about audio much, but this is using pretty standard workflow for recording audio. So all those free streams, they can be encoded and compressed. So for example, mesh can be compressed using Google's Draco 3D format. Texture map can be compressed with standard video compression technique, so it can be encoded with H.264 or H.265, and the audio can be also encoded as MP3 or AAC. And after we have those encoded streams, we can max them, we can wrap them in in a container, like MP4 in this case, and after that we have a single MP4 file which can be delivered, or it can be streamed to the audience. And on the client side we have either a player or a plugin, for example in Unreal or in a game engine like Unity or Unreal Engine, which then demaxes the container file, and then it decodes all the streams. And then after it decodes, it has it has polygons, it has texture and some audio, and then it can use standard computer graphics rendering to present it to the viewer. And this client, it can be either a web, it can be happening in a web browser, it can be happening in an application on a mobile device or on desktop, or it can be game engine if that's where the content is consumed. And currently each commercial system seems to have its own solution, so there are no widespread standards in use yet. MPEG 4 seems to support encoding of meshes and point clouds, so I saw some references to it, but I don't have much insight into that though. Currently there doesn't seem to be a lot of interop between various products. So in case of geometry-based free viewpoint video, the simplest but the least efficient way is to store geometry as a sequence of meshes, or alembic, and texture as a sequence of images. And this form of delivery is convenient for post-processing. So for example, for visual effects use or some games use, it's too inefficient for streaming or for real-time, or even for real-time playback in case of really high resolution data. And there seem to be an early efforts to improve the current situation in terms of interop and standards, and I include these two efforts here. So first one is universal volumetric compressed interchange format for free viewpoint video done in collaboration with Wild Capture Studios and others, and the second one is Volumetric Format Association, which is trying to address industry standards, interop, and specifications. So here you can take a look. It's the interesting compressed interchange format for streaming mesh sequences, and it also uses H.264 for video for textures. So this hopefully this will get used more often. But it's still early, but it looks quite promising. And then there is this Volumetric Format Association, which already includes some of the big players in the volumetric video field. So hopefully those efforts will help with interop and with standards of the deliveries or other steps as well. And in terms of mesh compression, so sequences of meshes with the same topology can be efficiently compressed. And since we don't need to store vertex connectivity information for each frame, we need to store it on topology changes, and when the topology is same, we just need to update the vertex positions. We don't need to update the triangulation. And some of the mesh compressions systems, they include Google's Draco 3D, then there is Open 3D GC, Corto, and Edgebreaker. So this is useful library if we want to compress geometry. Then there is this one, which I think is related to Kronos Group or GLTF, and they also show some. They show comparison with other systems, so this can be also used for compressing geometry. Then there is Corto, which is used by some of the systems, and here there are also they show some statistics of their compression, and there is also this edge breaker, which is interesting compression scheme for triangle meshes. So this is also often used in systems to compress connectivity. And once we have compressed our free viewpoint video or volumetric video capture, then it is ready for web streaming, and this is a really convenient way to deliver the content to really wide audiences, since it doesn't since it doesn't require any specialized application installation on the device. So any modern browser is able to play back those volumetric video captures in a web browser. And if we want to stream large captures or long captures, this content can be further chunked with Dash or HLS standards, and those can be decoded by web browser and a web player library, which then interprets the free viewpoint video data. And if we are talking about web streaming, then we are often using a content delivery network to minimize latency, and to talk about the motivation behind CDNs. So it takes light around 50 milliseconds to travel from New York to Sydney in the ideal case, and it's 100 milliseconds for a round trip. So we can see that this is quite long latency, and in order to serve a global audience, we need to have CDN, which means that those CDN servers, they are serving the copy of the content from a geographically closest server. So audience is in Sydney can access the data from Sydney server, which is much faster than accessing it from a, let's say, centralized server in New York. And to continue about web streaming and the technologies or examples that show that, so a lot of systems, they benefit from FreeJS, which is a JavaScript library which is often used for rendering of the encoded meshes or integrating them into the environment or manipulating them. And here I included a couple of examples of web streaming, and I really recommend to take a look at those links on your own device. I think in my case, since I am screen recording that, I won't get a really good performance, but yeah, here is our case study of projects we did for the fashion show. So we captured this model, and here we have web. We can preview the capture in web, so we can view it from any angle. And this might require a bit of buffering, but once it's buffered, we'll be able to see the motion, and we can also notice that the surface has quite a complicated dress, but the system was able to capture it really realistically. So we can see we have full control about the playback. And some other examples is so the next one is this one from Sense of Space. Here we can also see it has two different qualities. So thanks to that Dash or HLS encoding, we can also serve different qualities at different resolutions, and then the client, the device can pick the appropriate quality depending on the bandwidth that is available. So if the network is slower, perhaps then the client can pick a lower quality to ensure a smooth playback and a good user experience. So let's take a look at this capture.
already raised the state of mind. The feeling to be on the good way.
So yeah, a really nice example of the web experience. There is another web system. I'm wondering if I can see a live demo here. Probably just those screen captures. Ah no, here I can see. And maybe let's leave this buffer. Then there is another system. This is one from the Arcturus. So this
The internet brought our devices together. The web brought our voices together. The overlay brings us together, especially when we can't be. In the overlay, you can run a business, present a key.
So here we can see, a similar web player from a different system, and is also is showing a volumetric capture. Then there is the HoloStream product from Arcturus. So they are doing this tool set for volumetric video content creation tools, and they also have a nice web player. I'm wondering if I can find it here. Maybe just the video. So those web players, they can be also integrated into shopping websites. So you can imagine advertising your products in such immersive way, and this is also really helps with understanding proportions and reading the shape, since it's in 3D. So this is a really nice application, especially now in the current situation when it might be hard to get into the shops. And we can also see example of the AR experiences. So mobile devices currently, they allow for AR, either using built-in sensor from a device, or running SLAM in a browser, or remotely. And there is also a 8-wall service, which is really interesting, and they also have integration for volumetric video captures. So you can easily create those experiences with your content and preview it in AR in a mobile device without any application needed. So this allows for a really good user experience. There is also example from University of Surrey. So here they show multiple captures. We should also see different texture modes. Then here is a 4D views example, and they also allow for some relighting in the web browser. So I could imagine they are using FreeJazz or similar library to do the shading and lighting on top of the capture. And here is, while there's buffers, here is also example from Omnivore, a web player. Okay, I think while I am recording, maybe too much for my notebook. So yeah, let's continue with the geometry video. So while so far I was talking mostly about cases where the output of volumetric video system is a sequence of geometry or meshes, there is also similar approach called geometric video, which is a reconstruction and a representation of real people as sequences of 2D spherical geometry images. Geometry video providing a temporally consistent structure for level of detail and frame rate control in the free viewpoint video. So this is interesting representation, which allows for blending different different frames, changing frame rate, or it also allows for a native level of detail and consistent topology. So let's talk about it for a while. So here we can see two figures showing the reconstruction pipeline. So it's pretty similar. We start with multiple views, then we do shape from the silhouettes, and then after we do the surface reconstruction, we can do then mesh cutting to reduce the surface genus to 0. So you could imagine if the hand was touching the leg, then the surface genus wouldn't be 0 anymore, but if we can cut it to ensure that it's 0, and since that is a genus 0 surface, we can map it to sphere. And then if we have sphere, then we can have this 2D parameterization, which can store a texture, and it can also store vertex positions on each pixel. And then if we take those data, if we map it on a sphere, and then we can generate spheres of various triangulations or various densities. So this allows for a different level of details or various subdivision meshes to represent the quality. And if we can sample the 3D position to get the this matching world space position, and we can also sample this texture to get the look. And this can also benefit from alignment, which means that so in this example, in the top row we have unaligned geometry video, which means that for example this head part of the texture is in different areas, but if we align it, it's consistent, and this allows for interpolation of different poses or for retiming or various other applications and compression as well. So after we have so we talked about the most of the volumetric video pipeline, but there is still a step of post-processing geometry. So far we just captured, we faithfully captured the reality as it is, and then reconstructed it, and then you are able to present it in a web browser or on a mobile device. But in many cases we want to post-process it further to have more control about the content. And some examples, here are some steps that Intel did in their capture. And yeah, there are multiple things that can be done to both geometry and textures, and I will go over a couple of them. So in this example, we have this texture atlas of the capture, and if we know the target lighting of the experience, so if we know that the experience will be set in a, for example, in a game at the evening lighting, then we can bake this lighting into the texture, which means that we don't need to do any lighting calculation at the runtime in game, but we can pre-compute this lighting before and we can bake it into the texture. Or yeah, we can do the color degrading. Textures can be also delineated for more accurate rendering. So this is similar to photogrammetry delighting, and given that we have known geometry and known lighting, so for example we can capture HDR environment map of the stage as well, possibly at multiple locations. This information can help us with suppressing shadows, and especially hard shadows, because ideally we want to get rid of them or not capture them at first place. And packages like Unity or Unreal Engine or Houdini have interesting tools and presentations about this topic. So there is some information available on that, and there is also this lightweight introduction to the topic, which is article made by Artomatics. I think they are now owned by Unity, and they provide a suite of procedural tools for delighting, and I think for a couple of more operations on textures. So here they show intuitive introduction to the topic, and they show why this inherently a difficult step of this delighting. But here they show some of the results that their tools can produce. So this it's a good reading. And on top of it, textures can be also denoised, blurred, sharpened. Some colors can be keyed and shifted. So the usual compositing work. And given that often we are working with long sequences, with topology changes, then everything needs to be procedural, as driving manual tasks can get tedious, and yeah, that is caused by the change in UV layouts on topology changes. But again, like in the usual compositing workflow, some masks can be derived procedurally from world space positions or from normal angles, normal vectors, for example. And something we can do as well, we can key out parts of the clothes or skin that can be used in shading for adjusting shading parameters, so we can derive some PBR parameters for those parts. If it wasn't textured, like in the case of relatables where they produce a set of PBR textures. And so geometry can be post-processed as well. For example, props can be added or replaced. So we saw at the beginning of the presentation from the Kanadi et al. Where they introduced CG baseball into the scene. So this is the same principle. We can add or replace props that have been captured. So once it is in 3D, we have full control about the content. And for example, if we want to include additional props, then we need to know the motion of the character, and we need to track it. Sometimes it can be captured along with motion capture setup, or we can also hand animate props to synchronize their motion with the volumetric video. And post-processing on geometry can be tricky, especially because we deal with inconsistent meshes. So those topology changes means that we can't do certain operations, or they need to be geometry aware. And I will discuss some common geometry operations in the second part of this workshop, in Houdini specifically. And everything needs to be procedural, and we can see that Houdini is often used for processing such data because it plays well with those with building those procedural setups. And here I listed some ideas for tracking in 3D. So if we have our capture which is inconsistent, we need to track some position of the mesh in order to attach something to it, or to replace, or to modify it. And here are some examples to approach it. So we can always go back to original camera views, and we can do 2D tracking in multiple views. So you can imagine it as a Nuke's 2D tracker. We can pick a feature and we can track it. And if we have those tracks in multiple camera views, then we can reproject them as arrays into 3D space, and we can do it because we have calibrated camera positions. And if we have those arrays in the scene, we can either triangulate them, or we can, given that we have reconstructing geometry at that point, in many cases, then we can find intersections of the rays and geometry. Or another approach might include capturing attached markers which have easily separable colors. Then we can isolate those polygons that have this color, and then we can track them. And then we can also remove them. We can input them to remove the markers from the final capture. So these are some of the ways to approach tracking. And some other common operations in post-processing include making loops. So for example, if end and start of the loop have different topology, then mesh registration is needed for blend. And with the help of that, we can blend geometry, and we can blend texture as well, and we can do Volk cycles of the capture. So this is useful for games or when we want to have procedural animation. we can also separate actors, or we can combine them if they have been shot together or separately. But usually we will want to capture them separately if action allows for it, because if we add more actors to the capture volume, this brings in more occlusions, and this slightly reduces the texture quality. So if we want to maximize the visibility of each capture, we can show them separately and then we can combine them later on. And some other operations, they include smoothing or removing of some glitches or unwanted parts in the capture. So sometimes there are some processing errors which needs to be addressed later on. They can be, in many cases, automatically fixed. And we can also alter motion, so we can do some slight animation overrides on the capture. And with that we need some sort of consistent information. So if we have a matching skeleton which can be estimated, or it can come from a simultaneous motion capture shoot, then if you have this skeleton we can do animation overrides. And another approach in a model based system, so if we are using some priors of the captured geometry, so if we fit some parametric human models to the captured data, then we can often easily modify motion of the model, or we can regress joint positions, and we can do standard animation on top of it, and then we can propagate those animation changes back to the original capture. And there are a couple of presentations online which are showing example of workflows in Houdini. So this one presentation called Blade Runner 2049 and Coco VR from Costco to run at GDC 2019. They show Blade Runner VR project, and in examples they show is directional lighting baking in. So this is the capture they have, and this was captured at the Uniform Studio Lighting, but the final experience had this strong directional lighting, so they wanted to do high quality offline lighting, perhaps possibly in Arnold renderer, and then they baked it into the texture, and then in VR experience they were able to play it back in real time with this nice lighting. They also showed voxel-like transitioning example. So this is a common step where, since it is 3D data, we can do any sort of procedural effects on top of it. And there is another presentation about photogrammetry and volumetric video techniques by Will Discol and Danilo Moura Silva, also at the GDC 2019. And examples they show is changing heads direction, which is a common step to do, or color-based geometry separation, and general approach to processing volumetric assets inside of Houdini. In this presentation they also experiment with bringing in skeletons, which were possibly generated externally, maybe from 2D skeletonization. So systems like OpenPose can generate 2D skeletons which can be then brought back into 3D, or maybe they perhaps had a simultaneous mockup capture which gave them the skeletons. But the point is that if we have skeleton, then we can easily add in props, and we can modify either animation or look of the volumetric video capture. And then also then another step in the pipeline is rendering. So if we have if the client device has this volumetric video, then it needs to display it to the user. And in case of geometry based approaches, we render a sequence of meshes with an animated texture, and in the simplest case we use just a simple flat or unlit shading, since the texture has all the shading and lighting baked into it. So this is the cheapest and shows the realism of the capture, but this isn't that flexible because we can't do interactive relighting, for example. And if the 3D point video pipeline can produce normal maps, albedo roughness maps, then the PBR rendering can be used with the ability to relight and better integrate into the environment. So this is the standard games or VFX workflow use. And then another really important aspect of the whole production is delivery. So how do we get this? What are the different forms of delivering it, and how to engage audiences with this immersive content? And there are various delivery forms, and yeah, they include visual effects. So for example, in visual effects, those captures can be used in middle or background assets, and the visual quality in many cases needs to be improved or stylized for hero characters, but the quality is improving, and those captures, they are getting closer and closer to the camera. In terms of game engines, they are also often consuming or delivering this volumetric video content. And here I have two examples by Dimension. So one is a really nice project done in collaboration with Balenciaga and others. So this experience was remotely rendered in the cloud, and then the content was streamed into the device. So there is also a nice case study on Unreal Engine's website, so I recommend taking a look if you are interested. So here we captured a lot of characters for this experience, and then they were integrated into this really high quality game environment. But given this visual quality and this complexity of scenes, there was no way this could be rendered on mobile device. So it was rendered in a cloud instances, and it was streamed into the mobile device. So this was really nice examples, and yeah, those captures are coming from us. It has also really high number of captures in a game simultaneously. So it was a nice project. And let's see a couple of scenes from the experience. So it had some nice environments and graphics, and yeah, the humans and specifically their clothing were key to this experience, and we were able to capture many of them at scale and reconstruct it realistically. And this video also shows a stage that we used. So for capturing this project, we deployed our Polymotion stage, which is a mobile capture stage which can come to the talent, and it can do the processing at the location. And deliveries also include broadcast. So here is also a nice example that we did with Sky Sports. So this this project includes our volumetric captures, which are like live AR composited into the broadcast footage. So this allowed for really nice analysis of the technique or performance of the golfers. And here we can again see volumetric video of the yeah, we can see performance here, and I think I will show video in next slide. Yeah, so given this is a 3D, we can get really good insight into the motion of a golf swing, and I think here they show some examples. So yeah, the capture can be integrated with broadcast or virtual broadcast studio, and then it can be analyzed and presented immersively to the audience. So yeah, you get this nice example. Then there is also augmented reality is popular delivery medium. So here I have a couple of examples, and this one, social, and while speaking about augmented reality, so the social media networks, they also have really good augmented reality support with their apps. So from Facebook there is Spark AR application, which is sort of a game engine which lets you build very easily nice augmented reality experiences and then deploy them to their platform. And Snap has a very similar product called Lens Studio. And here is some example of our AR application. So I think I showed this already a couple of times. Another one is this one, this advertisement for Burger King. So it's featuring captured at our studios, and then it's presented in AR through a mobile device. And here is another example. So again, AR experience. Then another nice medium is virtual reality, and especially for location-based entertainment. So here are two projects done at Dimension. One is Jeff Wayne's The War of the Worlds. I think this experience is closed already, but it was really impressive and really immersive. So it includes this set, which combines use of VR headsets, and there are some lenticular displays as well, and some actors, and some fun stuff like hydraulics and some water splashes to deliver this really nice experience of this story. And it featured many captures captured in our studio, in addition to real actors. So it was really immersive, and we were able to produce a lot of content for such a experience with so many humans in it. So you can take a look at the videos if you want to learn more about it. And there is a similar one called the Viking Planet. So this one used also our captures, and it's a similar idea to the War of the Worlds. And when delivering, we often using web streaming. So it is most accessible, but it requires good connectivity, and AR is a good use case. And there is also work on the WebXR API, which will also help with at the end with the user experience of the audience. There is also this immersive healthcare training that we did, and it is also a nice example of.
So taking this stuff off is just as important as putting it on. And this is the point where you can contaminate yourself if you're not careful. So the most dirty part of you is the gloves and the front of your gown after you're aerosolizing.
So you can see this is really good to quickly explain important information, like in the case of COVID crisis, such educational content was really needed because things were happening quickly, and this is a really good medium of showing, of delivering training content. And important factor of delivery is also display. So how do we view it? So since it is 3D content, I think it's most appreciated in VR or AR, where we can get the illusion of depth, but it can be also rendered on a 2D device in many cases, or it also plays well with lenticular or holographic displays. So here are a couple of them. So Looking Glass Factory, they are creating those lenticular displays which gives us different views from different horizontal angles. So if we have 3D content, we are able to display it with the illusion of depth. Then there is the display from Sony, and there is also display from Voxon Photonics. And this example shows the capture done by Microsoft Mixed Reality Capture Studios, and is displayed directly on their display. And it is basically one layer which has projected video on top of it, and it's at high frequencies traveling up and down, and this gives us, thanks to the persistence of motion, it gives us this illusion of volumetric display. And this is also really nice case of showing volumetric video captures, since it takes advantage of its 3D nature. And there are, of course, some bottlenecks and limitations associated with volumetric video. So it is good in many cases, but it is important to know its drawbacks and challenges to know if it is the right tool for the problem. So to name a few, there is a cost consideration especially in high-end systems. And the cost is associated with setup, with operation and infrastructure. So it is using those volumetric video systems. They often require a lot of storage, a lot of compute capacity. They are difficult to operate. Many tools are really immature, and there is also in many cases there is a portability bottleneck. So many studios are tied to a specific location. They can't be moved easily around because they contain a lot of hardware. But one of the answers to that probability bottleneck is, for example, this polymotion stage, which we can bring to the talent and we can capture on their location rather than having them come to our studio. Then there is also scalability bottleneck or consideration. So in terms of hardware and software. So if we want to capture a lot of content, then we need to be able to scale up and to be flexible in that manner. And in terms of also of artists' work, so different projects, they require different control about the capture, and that implies a different amount of artists' work. And there are also quality limitations. So current 3D point video struggles with various conditions, and they include transparent materials, fine geometry like hair or glasses, or a golf club in this case, fast motion. We can't easily capture participating media, for example smoke, or transparent or translucent materials, or very reflective materials like shiny metal. So there are those difficult cases that don't reconstruct well, and therefore costumes or the captured content needs a visual or processing check before the actual shoot to make sure that everything will reconstruct well. And we need to watch out for aliasing. So we have limited resolution in cameras, so we can capture only certain frequencies in the for example in textiles. And in terms of continuing with quality, so many systems are lacking view-dependent effects, so lighting is often baked into the texture. So this is a consideration if we want to do interactive experience and we want to have interactive lighting, then volumetric captures. If we don't have a set of PBR maps, then we can't do the proper physically based lighting on top of them. And we might also miss high frequency geometry detail if we really want to be close to the capture. And yeah, I think we covered pretty well the high-level overview of the full volumetric video production pipeline. And then let's talk about the future. So what does the future look like? What are the current research trends? And yeah, what are the state-of-the-art results from various research groups? So current trends like recent advances in machine learning, differentiable rendering, neural rendering, radiance fields techniques are introducing new state-of-the-art results. Pretty much almost every week or every month we see that the quality bar of the free viewpoints video system is pushed. And those approaches can significantly improve quality of real-time systems as well, thus reducing the quality gap between the real-time and offline systems. And there is currently a great need for high-quality free viewpoint video or telepresence. And it's really a quickly advancing research field. So I picked a couple of works. There are many others. But I included a couple of them in this presentation. So one is neural radiance fields which have this internal neural representation of the captured volume as opposed to traditional point clouds or polygons. And what is impressive with their results is that they can capture fine geometry that they can capture inherently view depending effects, like we can see moving specular reflection. They can also capture refraction like in this example, so really difficult geometry. And they also support for this inward camera topology where we have a dome of cameras, so we can synthesize novel viewpoints from those. With this technique, it takes a bit of time to train, but the results are really promising, and it's still here we can see example of relighting. It's still early research, but the results are really impressive. Then this one is extension to the neural radiance fields, and we can see let's see some example, really impressive results given this sort of capture, so really low cost capture, and the results are really impressive. So here we can see novel viewpoints, and the system they can also output depth information, so we can see that it handles really well those difficult cases, so we can reconstruct them photorealistically. So these are all the limiting cases of the free viewpoint video, also refractive surfaces, shiny poster, and all those tough cases. Then there is also this one is really impressive. So this is monocular shape estimation. So it's giving really decent results, given that it's using only single camera view, I believe, and it can also synthesize believable backside of the capture. So this really interesting work, and the geometry is quite decent, given that it's using one camera view only. Here is also another really interesting research from Facebook research. so neural volumes, and they are trying to also solve some of the limitations with free viewpoint video. So in this case, they are able to capture the fine hair detail, they are able to capture smoke like at the beginning of the examples, and let's see some other examples. So they are really targeting those stuff captures like with refraction, volumetrics, and similar. It's it's still just a research. It's probably quite computational heavy, but the results are really promising. Then on the other hand, in terms of in the area of visual effects, the digital domain is doing a lot of work, and they are doing they're also using a lot of optimization and data-driven approaches to do facial animation capture and retargeting and constructing their for creating really high quality, high-end digital avatars. So if you want to take, you can find a couple of presentations online, and this one is also a really nice overview of their work and also showing the history of their system and how they progressed over time. Here is also interesting research, so capturing light fields, dynamic scenes as a light fields, and this this again allows for free viewpoint video, or we have in this case we have a free we have navigation range within inside of this sphere, so this allows for changing perspectives as well, and this is this outward camera topology example. Then there is also this example, I'm sure you haven't missed this one, so MetaHuman from Epic Games. So it's also a really nice tool that is really giving the power to create really realistic humans to wide audience of users. And there is also the Relatables project, which I mentioned already, which is taking advantage of the light stage to be able to infer shading properties. And here we can see infrared cameras showing the projected infrared pattern. They are lighting the capture with this alternating to gradients, which are then used for estimating surface normal maps, and they can be then well integrated into game engines or offline CG renders. And this is also interesting project. So this one is taking a free viewpoint video system which is real time, but
we present a system to enhance the output of a performance.
Because their input system is real time, it has some artifacts, and they are doing neural rendering on top of it to try to fix those artifacts. So they are trying to increase the realism on top of the system, which is real time but has some issues associated with it. But if they run this neural rendering on top of it, they can bridge this reality gap of the real time, let's say, offline rendering systems. So this is interesting research in that area as well. And to continue with neural rendering, so standard reconstruction approach like in the Relatables can be combined with neural rendering on top of it to increase realism. So reconstructed geometry and reflectance parameters are not perfect, so it's hard to reconstruct hair strands or complex shading. So we are doing in terms of geometry representation and shading, we are just modeling it we are doing many simplifications and assumptions. So it's really hard to realistically capture a scene. But neural rendering on top of it can work better with that imperfect representation and data to produce better results. And it can help with realism, or it can simplify acquisition process. So we could see examples that some systems works with one camera only, or even with a mobile camera, or they can remove the lighting requirements, or they can improve quality of real-time systems, which often suffers from artifacts, like we saw in the looking good example in the previous slide. And here there is an example from this presentation where they took the relatables capture and they further improve the realism by doing neural rendering on top of it. And I recommend this Eurographics this conference. There is a lot of very recent research presented. And on the other hand, while this is really helping with quality, neural rendering has some challenges to overcome, for example, generalization and editability. And there are a couple of more things. So this one is from CABU, it's monocular total capture, and this one is using model-based approach. So they're using those priors, and they combined multiple ones. So they use for face, for body, and for hands, and they combined it into one reconstruction. And it is pretty decent that given it is assuming it's monocular, it's using one camera view only. Then there is also mesh CNN, which is nice idea of applying convolutions on graphs, or more specifically on triangle meshes. So with this formulation of convolution, they can train neural networks that do, for example, they can do classification, or they can do segmentation. So also useful for tasks that are common with volumetric video. There is also another project that had nice results. So it's using multi-view capture, and it's trying to do this nice novel view synthesis, and it can handle well difficult cases like refractive surfaces. And there's also this really interesting project which is doing a really high quality segmentation, 2D segmentation in real time. So we saw that in case of volumetric video, we often use green screen to aid with segmentation, but with using a system like this, we could improve both quality and performance of segmentation. And yeah, getting good segmentations then has quality implications on the rest of the pipeline. And then I recommend watching those two sessions from the CVPR. So they are showing the very recent research in this area. And yeah, to name a couple of areas of application. So they include estimating shading properties, or doing view-dependent effects, or recovering lost detail due to limited camera reconstruction, resolution, or averaging, segmenting clothing, body parts, handling refractive fine detail participating media. So all those limitations of the current system, they're being addressed in the research. And yeah, let's talk about market. So what does a forecast or informed guess look like? So currently COVID is enforcing remote collaboration and accelerating demand for immersive content. So free viewpoint video growth is driven by demand for VR or AR content, and paired by the proliferation of HMDs. So sports, events, and entertainment application holds the major market share in the volumetric video market, and big tech companies like Microsoft, Facebook, Google, Intel, and others are investing into the solutions. And it will likely grow together with XR, and faster mobile internet, for example 5G, can also address the need for a good bandwidth, and this will help with user experience. And mobile AR is expected to grow too, and this will probably fuel the demand for volumetric video content, because if we are doing a lot of VR or AR stuff, then and we want to have humans in it, then we need to be able to quickly capture performance for that. And here are some some forecasts. So it looks like the market in that field is growing for the last couple of years, and it's likely to continue grow. And yeah, we are approaching end of the presentation. So to recap, we talked about what is a volumetric video. So we discussed fundamentals and concepts and papers behind the earliest idea. Then we talked about key properties of a free viewpoint video system. We talked about dimension and about approaches, and then discussed products, studios, tools, and then went over the full volumetric video production pipeline. So starting from capture, then processing, then coding and transmission, then post-processing, and then rendering it and delivering. And we also discussed bottlenecks, so the current limitations, but also a bit of the research field in that area and what are the future prospects look like. And I used many very useful resources for creating this this presentation. So if you're interested, they're often stated below the figures, but here are some of them if you want to take a closer look. And yeah, I think that's it. Thank you for your attention. It was quite a lot of content, but hopefully it will be helpful for you to now have a decent understanding of the volumetric video and what is it good at, what is it bad at, and what are good use cases for it. So I really recommend watching the second part of this workshop, which is the hands-on tutorial in Houdini. So if you want to see how volumetric video data looks in a 3D application, how it can be further processed, and also how to build a simple crowd scene, then you can find more in the second video. And yeah, thank you for your attention, and also many thanks go to Film Academy Baden-Württemberg and Dimension for the opportunity and support. And also I'm thankful to Mike Pelton and Charles Dupont and Marco Volino for proofreading and feedback on this presentation, and also Toby Hyder for the sample asset.